So I wanted to demonstrate the problems from section 1.3 with the imaginary numbers. So, first of all, let me back up and let me tell you about the imaginary numbers, which I know you watched the video earlier too, but just to make sure you got what an imaginary number would be, or how it fits in the categories of numbers. So we first of all start with a natural number. Those are the ones that we naturally count with, so sometimes they're called the counting numbers, like 1, 2, 3, so on. So if we think of, and there's infinite amounts of those, the counting numbers, or the natural numbers. Then when we add in the number 0, we call those the whole numbers. So they start with 0, the only difference, and then they count on 0, 1, 2, 3, and so on. So all of the naturals are also whole numbers. Then we got another layer we call the integers. Integers are the positive and the negative whole numbers. So they're all of these plus 0 and then plus the negative whole numbers, like negative 1, negative 2. So the negative of the whole numbers plus the positives of the whole numbers. Integers. Then we have one more layer that's still yet concentric, or including the ones before. And those are called the rational numbers. Rational numbers would be anything that can be expressed as a fraction. So all of these, we just put them over 1, and that expresses them as a fraction. Even 0 over 1 is 0. It's when 0 is in the denominator that it's not okay, but that's okay. So all of the, say, negative 7 over 1. Then we have fractions, and again, this is called rational, the rational number system. Anything that can be expressed as a fraction. That includes even a repeating decimal, like 0.3 repeating is 1/3. Rationals. Okay, then the first one that's kind of outside of that box over here, and there's really no size to it because they're all infinite, but let's say irrational. The opposite of rational would be irrational, and that's anything you can't express as a fraction. A real popular one, or I guess common one, would be pi. Pi is an irrational number. It cannot be expressed as a fraction. We approximated to 3.14, but it actually goes on and on and on. When you hit that in your calculator, you can see 10 digits of it, but it doesn't actually there. Let me find my pi button. So I don't know if you can see that well enough. Let's see. There we go. So pi is about 3.141592654, but it goes on and on and on, never repeating, never terminating. So it's irrational. Another one you'll use in this class later is irrational E. You will need that button on your calculator as well, and so your calculator will have that irrational E, and it is about 2.71828. All right, and we approximate that as well, but they really never stop. When you take all the rational plus the irrational, that makes up what we call the real number system. These are our real. So pi and E are real. They're irrational real, but they all, anything in here would be considered a real number. Now, what we're going to start in this section is the opposite of real, the imaginary numbers. Imaginary number set. And those are real easy to spot because there's an I involved. And it comes from the square root of a negative. The square root of negative anything would not fall in any of these categories. There's nothing times itself that gives us a negative number. So there is no real answer to that. So we define that as the imaginary unit I. And if we were to square both sides of that, I squared is -1. So anything that has an I on it is going to fall in the imaginary numbers. So say we're doing the square root of -25. That reduces to a 5 and an I, 5i. So imaginary numbers. Anything that has an I or involves the square root of a negative is imaginary. So when you take the real plus the imaginary, that's what complex is. So the name of our section is the complex number system. Complex means it's every type of number that we study here. The only thing that's not on the list is like 1 divided by 0. When you put 0 in the denominator, that is undefined outside of any of our categories. It's undefined in math. It makes no sense to divide by 0. And if you try that on your calculator, negative 1. I squared equals negative 1. Number 2 asks you what type of numbers are 6 plus I and 6 minus 5I. Whenever you have numbers that differ only by the middle signs, these are called complex, and then these are conjugates. Complex conjugates. So the word conjugate means that they're just opposite signs in the middle, and we're going to use that later in the lesson. Complex conjugates. All right, the product of a complex number and its conjugate is always a real number. Okay, so that's why we're going to use it, is we're going to use this trick and multiply. Sometimes we'll multiply by a conjugate so we can clean up something to a real number. We'll use that trick. So again, when you multiply complex conjugates, you always get a real number. What type of number is pi? So it is not imaginary, as I described earlier, and it is not non-real. We talked about how it's over in the real side. Everything that we do except dividing by 0 is complex, so everything's going to make that list, and it is on the real side. So it'd be those two things. I guess sometimes people want to think of pi as being more exotic than it is, maybe complex, or imaginary, but it is not. It is absolutely a real number. So it's in the real side. All right. Then you have some just basically moving on to work some problems now. So you can do these on your calculator, and I always encourage you to do so because it's good to practice with your calculator. You don't have to have a graphing calculator. That's not necessary in this class. You might find it handy, but it's not all that helpful because you really do have to learn the concepts to work them by hand to understand it, and the calculator can speed it up a little bit, but not that much. So, but in calculator, you should be able to use any type of scientific calculator and work this out. To do this by hand, though, I would bring out the negative side to kind of split that apart and think of that as being negative 1 times 100. The negative part of it, the square root of negative 1, by definition, is the imaginary unit I. So basically, just if you have a negative sign under a square root, you're going to have an imaginary unit I involved. Then do of the other part as normal. The square root of 100 can even to be. Normally we write it in that order 10I, but I10 is fine. The next example we know will have an I involved, and then we'll reduce the square root of 112. Off the top of my head, I'm not really sure what goes into 112, but I feel like it must reduce. So let's check that out on our calculator. Looks like 112 will divide by some perfect square. So I'm checking out my perfect square list, like 25 is a real common one we use, but 64, 49, 16. I bet it's 16. 112 divided by 16. There it is. 16 times 7 is 112. So we can break this down into 16 times 7. And let me get that out of our way. So the square root of 16, because it's perfect, we can reduce that out of the radical. The 7 will stay in, and then don't forget to put your I somewhere. It can go in the middle. Sometimes you see it on the end. Somewhere, those don't have to be in necessarily any particular order, but there should be a 4 out of the radical, a 7 left in the radical, and an I for the square root of the negative 1. All right. Next example, we're multiplying complex numbers. You might just reason out that anything times itself is like squaring a square root, and we'll bring out the negative 7. That's one reason it's negative 7. The more complicated reason, I would say, is if you did this step by step, would be that negative comes out as an I. So you've got I radical 7, plus this negative comes out as an I radical 7. Then I times I is I squared, and radical 7 times radical 7 would be radical 49. We learned that I squared is negative 1, so that's negative 1 times the square root of 49 is 7, and there we also can confirm the answer negative 7 makes sense. Number 8. We can divide, and kind of example, but maybe a little different reasoning. You can that. And this time, instead of I times I squaring, the i's are divide out. You'll imagine part on the other. Then we can think of this as being all under one radical and reduce that fraction. I'll try that first. I'm going through this with you as exploring as well. So that does work out evenly. That would be my first thing to try. If it wouldn't have worked out evenly, I would have worked them separately and reduced that way. But 320 just happened to divide by 64 perfectly as 5, so we're able to reduce it to square root of 5. All right, number 9. Example 9. These may not line up exactly with your homework, but it should be pretty similar to what you see in your homework examples. To do this is leading up into our next section when we talk about the quadratic formula and how we reduce that. A part of the quadratic formula is this radical part right here. Now, you can go ahead and divide that to a 4, but just don't forget this is also divided by 2. So this is divided by the 2 as well as this is divided by the 2. So if you cancel that out and say 4, don't forget the 2 is still there to divide this side. So we usually just recommend you don't divide until we get this thing simplified a little more first. So the first focus is on this radical. Just like we did above, we will reason out that there is an I, and then we'll try to reduce 128. So I'll take my calculator and start typing keys. I think 64 times 2 is 128. It sure is. So we could think of that as being 64 times 2. Break that apart. And then the square root of 64, because it's perfect, comes out as an 8. So we have an 8 and a radical 2 and also the I out of that. So it looks like 8 minus 8 radical 2, then I here all over 2. And then we reduce all these parts reduced by 2. Don't really conclude that, just the coefficient in front of that. There's just 2 terms, both divided by 2. So 8 divided by 2 is 4, and then this 8 also divided by 2 is 4. So we get rid of any denominators, and that's our final answer. Do it again on number 10. Sorry about that. On number 10, same thing, we've got to reduce this radical by bringing out the I, and then 12 will divide to 4 times 3. The square root of 4 is 2. So we've got negative 8 in front plus the 2 and a radical 3 in any order over 40. Now this one not as evenly, but I can reduce 8 over the 40 and the 2 over the 40 separately. The 8 over the 40 will reduce to 1/5. And then the 2 over 40 will reduce to 1/20th, right? And then we've got I radical 3. And actually, when we write these, the directions say they have to be in A plus BI form. So we do need to have 2 separate parts. We could not have kept that as all one fraction anyway. We have to have the real part separated from the imaginary part. All right, number 11, we're adding imaginaries. You add imaginaries almost like you do like terms. There's nothing to distribute in front of either one of these, so you can kind of just drop those parentheses and combine the like parts. 7 and 9 is 16. 8i and minus 7i is minus I. And they do need to be in that order, A plus BI order, so the real part's always in front and the imaginary in the back. All right, one more like that. It's very similar. It's an addition. So 3 and 6 is 9. And then 6i, positive 6i, and minus 5i is positive 1i, or just I. So 9 plus I for that example.